if we don't, I do have information here in the slides that you'll have available to you. And of course, there's, I think it's section 1.4 in the reading. So this is chapter 1 in the text. I think 1.1 through 1.4 is the content. And then you'll notice that 1.5, 1.6, and the material afterwards are intended for student projects and or homework questions. So the reading is just those first 4 sections. Let's get started. I already described the basic outline. So in a class on probability and statistics, probably the best thing to do is to ask yourself what those terms themselves mean. We probably all have some kind of an intuitive feel for it, but let's start with probability. What would you say is probability? If my 10-year-old were to stop by and ask, what's probability, what would you say?
The chances that you have of getting something.
Okay, good. So if we want to know how likely something is to happen, or how likely a certain outcome might be, that's essentially what probability is there for. It's the theory of how to deduce the likelihoods of different outcomes. Excellent. How do we find those probabilities? Interesting, harder question. So there's actually multiple ways we could do this. Oh, someone having a thought they want to chime in? I'm perfectly fine with that. Okay. So there's multiple ways to find probabilities. In fact, there's multiple perspectives on it. One way is we could model a situation based on what we think individual probabilities are, and then we can use mathematics to build combined probabilities. So for instance, if I am flipping a coin, I might decide that the probability of heads is 1/2, and the probability of tails is also 1/2. That's what I mean by a fair coin. Now, if I pick up a coin, is it necessarily a fair coin? That's not certain. That's a different question. But if I want to use a mathematical model, I might assign the probability of 50% to heads, 50% to tails, and then I can use that with some basic understanding of mathematics to build more extensive probabilities, similar to what we saw with the Bogdan's calculator earlier today. On the other hand, I could also collect experimental information. I could flip that coin 100 times and record how many times I get heads and how many times I get tails. If I get heads 52 times and tails 48 times, I might decide, well, I think the probability of heads is 0.52 and the probability of tails is 0.48. It's pretty close to what I said mathematically, but it's not the same. And I deduced it from looking at what happened in my experiment. Now, if I were to use that idea, I would probably want to test it a lot. 100 would probably not be sufficient. It turns out people have actually done this with coins, and flipped a coin tens of thousands of times, I believe. And anyway, it turns out I think that quarters in the U.S. are not exactly fair. I think the probability of heads is ever so slightly, like 50.1% likely to come up heads, versus 49.9% likely to come up tails. Essentially 50-50, but not exactly the same. So interesting things. All right, well, that's probability. But the title of the course is Elementary Statistics. So what about that? What about statistics? What is that? We're going to start with the really hard questions in the class. All right. Well, so there's a number of things we could use as a definition for statistics. I'm going to stick with the one that our book uses. I like theirs best from all the books that I've used over my time teaching statistics. It's a science, actually, and it's the science of collecting, organizing, analyzing, and interpreting data for decision-making purposes. Well, not enough coffee in the world today. What can I say? When it comes to statistics, there are two major types that we'll spend some time with. Descriptive statistics, that's essentially describing the structure of the data, and we'll talk about types of things we might do there, but we could do things like computing an average, describing the median, the interquartile range, those kinds of things. We could also have certain types of displays that are descriptive. That's descriptive statistics. And we could also have inferential statistics. And that's where we're actually trying to deduce something from the data that we collect. We're trying to decide whether something is true or decide about a structure that we don't fully understand, collect information from our data, and then run it through some statistical processes to make decisions. So descriptive statistics, that's essentially organizing and summarizing. These are a couple of examples of ways I might do that. I might summarize that information in bar chart form. This is a comparative bar chart. I had two different schools comparing students that are full-time versus part-time, and the color coding and the pairing in this way makes it easy to compare the two institutions and also the two types of students. You might also use a pie chart to describe what fraction fall into different categories. And so in this case, we might look at statistics students in a certain class and ask how many are in which stage of their collegiate career. And in this case, it looks like about 2/3 are freshmen, and so on. And so there's different properties for each of those. We'll talk about some structures for those particular charts in just a few moments. Inferential statistics, again, is drawing conclusions from the data that we have. And it is important to be able to collect good data. We'll make that more formal later on. But the methods that we use to do that are what we mean by inferential statistics. And so one example is what I tried to show you a little bit of earlier with Desmos, and that's producing a least squares regression line of best fit. If I have a large collection of data and I seem to notice a generally linear structure, I might produce a line to model that relationship, and then I can compute information about that line to tell me how well that line explains the behavior I observe. Obviously, it's not a perfect fit in this case, but you can tell it's reasonably good. And the R squared value, we'll learn how to interpret that formally, will give me a feel for how much of the variation in this data is actually explained by the trend of this line itself. All right, and so here's a more formal statement on what probability means. It's basically just the mathematics of randomness and chance. It's calculating the likelihood that a particular event might occur, and this example is very similar to the one I just said. If you toss a fair coin 4 times, on average, oops, sorry, my computer does that a lot. On average, we'd expect 2 heads and 2 tails, but of course, that won't happen every time we do it. Right? Sometimes I'll have 3 heads and 1 tail. Sometimes I'll have 4 heads and no tails. And sometimes the reverse will be true. But if I toss the same coin 4,000 times, chances are it's going to come out pretty close to 2,000 heads and 2,000 tails. Maybe not exactly that, but within a few. Much closer than the 4-coin example might. And that's our first example of a place where thinking through the idea of large sample sizes, it helps to smooth out some of that variation. And so we would expect to see some variation, but not a ton. If it's truly a fair coin, we'd expect to see things pretty close to 50%. And the real reason why we pair these two things together is that, especially when it comes to inferential statistics, we actually use the theory of probability to deduce the likelihood that certain events will be observed. And then we collect data and compare what we see in that data to what we'd expect based on the assumptions in our probability model. If those two things agree, then okay, we can't really conclude anything new. On the other hand, if our probability model tells us one thing and the data we see is totally different, totally unexpected, then we can actually realize that our original model that we built that probability on is incorrect, and then we change our assumptions. And this is actually the fundamental idea for hypothesis testing. We'll set up something called a null hypothesis where we decide maybe I think these two groups are exactly the same on this one characteristic. And so I will collect data, and I find, lo and behold, 90% in group A have this characteristic, and 60% in group B have this characteristic. And if those two groups are large enough, I can actually conclude that that difference is pretty significant. And so, in fact, they're not the same. And I do that by building a model based on how much variation I would see from sample to sample in those two groups. And if the 30% gap is much bigger than what I'd expect to see, then I throw out that assumption that they're the same. That's just basically the idea that we'll be doing.